Hello, statistics students. Let's jump right in on conditional probability. So P of B, and I don't like it when we say P of B. People don't really know what that means. When we read it, let's read what it really means. The probability of event B occurring. That's what that means. When we put a line there and then put an A, that means the probability of B given that A has already occurred. Or you can say it's the probability of B occurring given or on the condition of A already occurring. So conditional probability. So if we're flipping a coin, the probability of heads is 1/2 if we have a fair coin. What is the probability that we flip a heads given that we just flipped tails? Well, that's also 1/2. In other words, the fact that we already flipped tails has no bearing on what we're going to get this time. So flipping a coin is an example of independent events. I could flip 5 heads in a row. The probability is still 1/2 that I'm going to flip a 6th head, assuming the coin is fair. So independent events are events where the outcome of one event does not affect the outcome of another. And if it doesn't affect, then we get some simplifications. So the probability of B occurring given A is equal to the probability of B, because A doesn't affect it at all. And our example is, if we've already flipped the tails, the probability of getting heads given that we just flipped tails is it's still 1/2. It's just the probability that we'd get heads. And in this case, if you write it, you notice here it's B given A, here it's A given B. Here, B doesn't affect A at all. So the probability of A given that B has already occurred is just the probability of A. So the next part of this lesson requires that you understand a little bit about a deck of cards. Now, I've just talked about a definition of independent where one event does not affect another. So let's take a deck of cards and draw one. What is the probability that that card is a 3? Well, there are 4 ways of getting a 3. There are 52 cards total. So the probability of getting a 3 is 4 out of 52. Slide that card back into the deck. Now now draw it again randomly. Now what's the probability of getting a 3? Well, it's still 4 out of 52. The probability hasn't changed. When we're dealing with a set of playing cards like this, we call that with replacement. And events, when we do it with replacement, are independent because the probability doesn't change. The fact that we already got a 3 this time, or whether we didn't get a 3, doesn't matter. After you slide the card back in the deck, the probability of getting a 3 hasn't changed. But if you do it without replacement, these are dependent. This is where the probabilities change. So we're going to draw 1. The probability is getting a 3 is 4 out of 52. Let's set that card aside. We're not going to replace it this time. Now, if it was a 3, what's the probability that we'll get a 3 now if we drew? Well, there are only 3 3s left out of 51 total cards that are remaining because we put the 52nd card aside. So in this case, drawing a 3 the first time did affect the probability of drawing a 3 the second time. So that is a dependent event. That's without replacement. Now, we've already learned the fundamental counting principle that says if one event can happen in any of m ways, and a second event can happen in any of n ways, then the number of ways those 2 events can happen in sequence is m times n. Similarly, you can think of P of A and B. So the probability that A and B occurred, and one way of thinking about it is the probability of A and then B occurring. That's happening in sequence. You multiply the probabilities together. So the probability that A and then B occurs is the probability that A occurs, and then the probability of B occurring given that A has already occurred. Now, if they're independent, the A doesn't affect the B, and this just simplifies to the probability of B. So the probability of A and then B, if they're independent, is just the probability of A times the probability of B. And yeah, we'll do some examples. Like this one. Let's draw, let's take a deck of cards, and I want to know the probability of drawing a king and a king with replacement. Well, with replacement, you recall, the probabilities don't change. There was a 4 out of 52 chance of drawing a king the first time. There's a 4 out of 52, because you put the card back in, there's a 4 out of 52 chance of drawing it the second time. So that multiplication simplifies to 1 out of 169, or 16 out of whatever that is. But without replacement, the probability of getting a king the first time is 4 out of 52. The probability of getting a king the second time, given that you got one the first time, well, there are only 3 kings out of 51 left. So you multiply those. And you see that the probabilities are quite different. So the question is the probability of B given A, or B given that A has already occurred, equal to the probability of A given B? And to help you remember that, I came up with this little example. Is the probability of getting wet given that you went swimming equal to the probability that you went swimming given that you've gotten wet? And the answer is no. The probability that you get wet given that you've gone swimming is 100%. It's 1. But what is the probability that you went swimming given that you're wet? Well, a lot less. Maybe you took a shower. Maybe it rained. Maybe someone hit you with a water balloon. So there's not a 100% chance that anytime you're wet, it's because you went swimming. So what I want to do is point out here that conditional probability only goes one way. B given A does not imply A given B. So in our current book, on page 152, problem number 7. Here's a bunch of information we're given about people at a college. You have your men and your women, and some are nursing majors and some are non-nursing majors. So if you take a person at random, what's the probability that you choose a woman? Well, there are 2,407 women out of 3,605 total students. That's the probability that you get a woman. If you draw a student randomly, what is the probability that that person is a nursing student? Well, there are 819 total nursing students out of a total of 3,605 students. Now, what is the probability that you've chosen a woman given, or that you choose a woman given that the person you've chosen is a nursing student? Now, we're not dealing with 3,605 students anymore. Given that they're a nursing student, we're only dealing with 819 students now. So what's the probability that we choose a woman given that we've chosen a nursing student? Now that probability is 725 out of 819. What's the probability that we choose a nursing student given that we've chosen a woman? Well, I'll cover those up so we can still see the titles. But now we're only looking at these 2,407 women, because we're given that the person's a woman. So now the number of nursing, the probability that we've chosen a nursing student, given that we've chosen a woman, is 725 out of 2,407. Clearly, these are not the same number. So again, that tells me that conditional probabilities only go one way. So female given nursing is not the same probability as nursing given female. So that's a start on conditional probability. Let's look at a few more. Here's some things that we want to look at. So, number 24 says, in a sample of 1,000 US adults, 150 said they are very confident in the nutritional information on restaurant menus. 4 US adults are selected at random without replacement. Find the probability that all 4 adults are very confident. All right. So we're doing it without replacement. So let's let A be the probability that the first person chosen is highly confident that the menu information is correct. So the probability that the first person that we've chosen is highly confident is 150 out of 1,000. Now we set that person aside. Now B is the second person is highly confident. The probability that the second person is highly confident, given that the first person is, well, now there would only be 149 highly confident people left out of 999. So that's probability of B given A. The probability that the third person is confident, given that the first 2 are, would be this. And the probability that the fourth person is confident, given that the first 3 are, is this. So the probability that all 4 of them would be confident, we're going to do the multiplication rule, just multiply those independent or those dependent events together, but we've accounted for all the conditional probabilities. We're going to multiply them together. Would be very unlikely. This is saying there's a 15% chance. This is a little bit less than 15, a little bit less than 15, a little bit less than 15. Yeah. This is like 1/20th of 1% by the time you get there. Now, question B says, what is the probability that none of the adults is confident? None of those 4. Well, that means the probability of A prime, if A was the probability that the first person is confident, A prime is 850 out of 1,000. Again, without replacement, what is the probability that the second person is not confident, given that the first person was not confident? And we keep doing that in that pattern, and then multiply the numbers together, so there's slightly over 52% chance that none of the 4 people that we chose would be confident, highly confident. Part C says, what is the probability that at least 1 is highly confident? Now think of that. At least 1, that means 1 could be, 2 could be, 3 could be, or all 4. Wouldn't it be easier to find the probability that none of them is confident? That way you only have to do 1 calculation and then subtract it from 1, because that would be the complement. The probability that at least 1 is highly confident, the complement of that is the probability that none is highly confident. And you know, if this plus this equals 1, then this equals 1 minus this. That's the nice thing about complements. So we've already calculated in the last part that the probability that none of them is highly confident is this number. And then the probability that all 4 are highly confident, we've already done that. Now, there is also Bayes' rule. And Bayes' rule is at the top of page 156. And I've included, at least in the year I'm making this video, I've included a couple of documents about Bayes' rule in my Google Classroom. And the first one is about Bayes' rule and breast cancer. So if you have that video, or if you have access to that document, I'd like you to read the document. We'll actually go over it in class. Here's some information that you'll need. We're going to call B positive the event that a patient actually has breast cancer, and B negative the event that they don't. D positive is that they're diagnosed with breast cancer, and D negative is they're not diagnosed. So what we want to know is, what is the probability that a patient, if you're choosing somebody at random, not somebody who has a history of breast cancer in their family, things like that, but what is the probability the randomly chosen person would have breast cancer if, or given that they were diagnosed with it? In other words, they had a positive mammogram. You might think it's really high, but as it turns out, given these numbers, according to my document, it's only 7.5%. And I'll explain it in class, but the reason why it's so low is false positives. Here are the actual calculations based on the numbers that are in the document and on the last slide that I just showed you. The second document, also about using Bayes' rule, was about polygraph tests. And so I'm using these symbols because they make sense to me. Plus means that the polygraph is registering positive, you're lying. Polygraph says you're lying. Here, the polygraph is indicating that you're not lying. T is the probability that, or is the event that you're telling the truth. And L is the event that you're lying. So based on the information that was given in the handout, and I took this from a mathematical statistics and data analysis book, got that information there. Here's some information. The probability that the polygraph says you're lying when you're actually lying is only 88%. Which means the probability that the polygraph says that you're not lying when you actually are lying is 12%. That's a pretty big discrepancy in my book. The probability that the polygraph says you're not lying when you're telling the truth is only 86%. And then the probability that you are, or that the polygraph indicates lying when you're telling the truth then naturally comes out to 14%. So let's say that you're interviewing a large number of people. Again, it's on the handout, and 99% of them are telling the truth and 1% are lying. What is the probability that somebody's telling the truth given that the polygraph says they're lying, given that the polygraph is giving positive, you're lying? Turns out there's a 94% chance. If these numbers about the polygraph out of this book are accurate. So it turns out, it says that I've written this is 94% of the positive polygraph readings will be in error. So 94% of the positives will be false positives. And anyway, we won't go into that. Then, on page 156, there is the birthday problem, which I've described before, and I've looked it up. It is 23 people. So what is the probability that no two people in a room would have the same birthday? Well, one person, this is the probability that nobody else in the room has a birthday. If there's a second person in the room, the probability that this person does not have the same birthday as this one, assuming again we're talking only 365-day years, is this probability that the third one, and we're just going to keep going on and on and on until these fractions all multiplied together are 50%. So that's the probability that no two people have the same birthday. The complement of that is the probability that at least two people do. So the probability that at least two people have the same birthday is 1 minus the probability that nobody does. So if all of these equal about 50%, then 1 minus that's going to be 50%. And then you count, and there will be 23 of these fractions. Okay, play a little algebra here. We learned that this is the multiplication rule for probabilities. You can divide both sides by the probability of A. And now the probability of B given A is just the probability of A and B, which is the intersection, divided by the total probability of A. It's important to remember that A is just not this little piece over here. A is this entire circle. And then B. So if we want to know the probability of B given A, it's like, okay, assume A has already occurred. So now we're not looking at B anymore, we're only looking at A. Now, what is the probability that you would get B? Well, it would be this fraction over here of the entire circle. So that's the probability of A and B divided by the total probability of A. Well, that was long. Hopefully some of the problems were interesting. And if you're in my actual class and get those documents, I think you'll find the polygraph and the breast cancer ones to be interesting or scary, whichever way you're looking at it. But other than that, nope, I'm done. I've got it all. Have a great day.